Okay, we've had the first derivative test, which does what for us?
It teaches us derivatives.
Sir? Increasing, decreasing, and that led us to minimums and maximums, right? Okay. So now we get into, it's not enough to know just the minimum, maximum. We want to know, if we were sketching a graph, we would want to know this concavity too. In other words, is that thing curved down or is it curved up? And then we get into the second derivative for that. So you look at these notes and it says, just what it's saying. It's kind of obvious when you're looking at a picture. And the thing I highlighted is, where's the tangent line in relation to the curve? If those tangent lines are above the curve, like up here, then yeah, it's decreasing in that particular thing, but it means it's what? Concave down. If the tangent lines are below the curve, it means it's concave up. Okay, so no big deal there. So we want to find the open intervals where this function is concave up or concave down.
Would it not be the same as just when it's increasing or decreasing?
Not necessarily. That's a good question. I mean, I could have a function that's doing this, right? I could also have one that's doing that. They're both increasing. Good question. So it's telling us we're going to do this second derivative kind of idea for concavity. And it's going to be really, really analogous to the first derivative test that we did. So look what it's saying. If x double prime, meaning we're talking about f double prime here, second derivative. First of all, does it exist? If it does, then if it's positive, then the graph is concave up. If it's negative, the graph is concave down over that interval. It's all about an open interval here, this. So how do we do this? Well, it's going to, again, be like the first derivative stuff we did. You're going to say, all right, let's find our critical points for the second derivative. And then we'll test them and we'll know over those intervals. So let's do one. First thing we do, we got to find the first derivative first. So this is a quotient rule, and notice that first term in the numerator is going to drop out, and that part. Okay, all of that's over this thing squared. Good so far? Check my math. Always. That'll condense to this.
We want to oil the bottom?
No, sir. Just leave it. Good question, but just leave it that way for right now. So now what do? I've got a rational function.
Set in the quotient rule.
Am I done with this one?
No, you have to. That's your first derivative.
Yeah, it's first derivative. So I can find out where my critical numbers are for the first derivative. And I'm getting 0 for I've got to do the numerator and denominator separately, right? So the numerator, I've only got that 1. Now, what are we looking for in the denominator? Yeah, exactly. Is there anything that will make that denominator 0? Square root of 3?
There's second. I mean, multiplying it by 0 would make it 0.
Yeah, but I mean the way it is right now. Is there any value of x that would make this denominator 0?
X equals
Because we're squaring x.
X. So real.
We're squaring the whole thing.
There's no value to make it 0.
Right. So what's my critical number for this thing? Just 0. So now I'm going to get the second derivative. I'm basing it on the first one, so I've got to take this thing we ended up with out here and get the derivative of it.
Why can't we do anything of it just because X there's nothing X can do to the denominator 0?
Yeah. So it means our critical number is just that x equals 0 for the numerator.
It's just the same thing.
Yeah.
Thank you.
Sure. Okay, second derivative. This is a slightly more complex quotient rule. And it chains out like that. This thing is rife with chain rule. All right, so now what? I put all of that over the original denominator squared, which gives me x squared plus 3 to the 4th. I start just, here's what I did on the numerator. I'm seeing, actually I just arranged stuff. I moved the negative 12 out front, and then right here, I'm just scanning down the line so I don't have to take up 3 pages to do it. So I've got a 2x here, a 2 here, and a negative 12x there. So I just combined that 2x, that 2, and that negative 12x, and I've got plus 48 because of that, which simplified it quite a bit. And once again, all of that's over what we had before. And if you just want to write same there, that's great, because sometimes those denominators get really nasty. So then I looked at that, and I said, well, I've got some things I could pull out. I'm seeing 12 and 48. 48's a multiple of 12. And I'm seeing this x squared plus 3 to the second power and to the first power. So what I did, I'm not saying this is the only way to do it, but what I did was I pulled out a negative 12 times x squared plus 3. And that leaves me this. And how would I check to see if I did it right? I would just multiply this stuff together and see if I got what I started with over there on the left. If something doesn't make sense, we'll holler.
You cancel out that x squared plus 3 now, so you can bring the denominator down to x squared plus 3 cubed.
Good call. I can cancel those and get that. So it's getting simpler. Oh, don't do that. Bless you. All right, on top.
So do we set the numerator and denominator to 0?
We don't set the denominator to 0. We don't want it to be 0. We're going to see if there's a value that'll make it 0. Is there a value of x that I could plug into the denominator that would give me a 0 down there? No more than it was up there for our first derivative. But the top, I can combine like terms. This one takes a minute. Getting closer. Now I would set the numerator to 0 to see if we got any critical numbers there. They're going to help us out.
There has to be something where the stuff in the parentheses, stuff in the parentheses will equal 0.
Sir?
Plus or minus. The x has to, x equals 1. Plus or minus.
Yep. I'm putting all the steps in here, but I mean, obviously, if you get to x squared equals 1, you can cut to the chase, or 3x squared equals 3. So we got two critical values, critical numbers there, as many as there are. On our first derivative, how many did we have? That's a good question. 1. Here, I've got 2 for the numerator. We don't have any that pop up for the denominator because there's no value of x that'll make it 0.
How do you know when we have all the critical numbers? Other than just using the thing. So the online calculator thing, I don't remember.
You don't get to use that on a test.
Well then, how would we know how?
Did I factor the numerator? I mean, that's not a bad question. Did I factor the numerator?
Yes.
Did I find all the places where that numerator equals 0, all the factors of the numerator? Then I'm done.
But if we can derivative this for as many times as we want, when do we know we're done?
We're only going to go to the second derivative. That's what we're talking about today. Now, could this one have more than 2 derivatives? Yeah.
It does have more than 2 derivatives.
We could go nuts with them. If I wanted the third derivative, what would I do? I would take this thing right here and do the quotient rule on it. With quotient rule stuff, it just gets nastier, nastier, nastier. If you've got just a regular, like x squared plus 3, how many derivatives could I get out of that? First derivative would be what? 2x? Second would be 2. After that, what's every other derivative? 0 all the rest of the way. See? So depending on how complex your original function is, you might have a ton of derivatives. It could go on forever. That's not a bad question. What if I had f of x, just to make sure we're talking about the same thing? What if I had f of x equals something simple? How many derivatives can I have? Right. Yeah, it's going to flip back and forth between sine and cosine. The signs are going to change when you hit the cosine, the derivative of it. Okay, so then what do I do here? Well, what did we do with the first derivative? We did, which is, I guess, what you just said. Yeah, where'd my 0 go? It is. Oh, no. That's first derivative. I just wanted you to see that the critical number for the first derivative was 0. No, I just threw that in. I want to make sure that we know how to do it. Okay. Sorry about that. That was confusing. All right, so I've just got 2 critical numbers for the second derivative. Yes, sir. From the second, not necessarily from the first. Okay, that was my bad. Well, we'll share the guilt. Okay, so I'm going to pick numbers to the left of -1, in between those 2, and to the right of +1. So these are the ones I picked. So when I'm looking at a -2 plugged into this thing right here, what have I got? I've got a -12. If -2 is substituted for x, then I've got -3 times a positive number, which is -12 plus 3. So I've got a negative times a negative divided by, that bottom number is always going to be positive. So positive. So that means what? Yeah. So with that being positive, just what we talked about so far, and I know this is new, that says what? That graph is concave up.
So reverse. So like negative on the top, It's gonna be negative on top because yeah, no, it's gonna be positive on the top because positive, negative times negative, positive and positive.
Yes.
So it like that or the
We know that it's concave up. Yeah.
just me.
Yeah.
And it'll be the same for the
We're kind of thinking that. So for the 0, if I plug a 0 into that, I've got a negative 12. If x is 0, I've got a negative 12 times a positive 3, which is negative, divided by a positive, which is a negative, which gives us negative there. So we know it's concave down. And then last but not least, like the man said, if we plug a 2 in, then I've got negative 12 times negative 12 plus 3 again. So that's going to be positive divided by, negative times a negative, which is positive divided by positive, gives us that. Stop right there. So we're thinking, based on our second derivative shenanigans here, that this graph is going to be concave up from where? Let's write it down, because this really is what it asks us to find after all that. So we're thinking concave up from negative infinity to negative 1, and then it picks up again 1 to positive infinity. And I put the union symbol in between because there's a jump in between. There's a gap there. And then the concave down part is that middle. And what I did was I went ahead and graphed this in Desmos so that you could see what it looks like. So there's our original function. Does it match up with what we found? Let's go back. Look at this critical value right here. Now it was first derivative. It says something's going on at 0. Now we didn't say, to the left of 0 was it, but we know at 0 something's going on just from the first derivative. Something is. And if we did all the first derivative stuff that we've been doing, we would have found out, okay, that's a relative maximum. Here I went ahead and graphed the first derivative function. That's what it looks like. And we're seeing where's its critical number? Right there. And then I put the second derivative graph in. So it's saying, now look what it's saying. To the left, here's negative 1 right here. It's saying to the left of negative 1, in other words, smaller than negative 1, what's the concavity? Is that green line above the x-axis or below? Right here at 1, to the left of 1. To the left of negative 1, sorry. It's above. That means it's concave up. And that's what the original red line is doing. Look at it to the right of negative 1. Okay? And that's back up again.
So can you find the negative derivative?
The green line is what we're talking about. Look at the blue one. I'm thinking maybe y'all haven't realized.
Is the question, isn't the question on question 1 representing the blue one because it's concave up, concave down?
The blue one is our first derivative function. So let me write that on there. So this blue line is f prime of x. The red one is just f of x. This green one is f double prime.
If that's the case, why is it going down past 1? It's concaving. It hits concave. It's concaving up at 0. So it's concaving up at 0, isn't it?
It switches. And that's going to be called an inflection point. Somewhere in here, and it tells you where. Right here at x equals 1. -1. I keep saying 1. At x equals -1, if we zoomed way in on this, you'd see that it went from being concave up to concave down. Because that's what, from -1 to +1, isn't that thing concave down?
Yeah, but what about?
These are called inflection points, and we're going to talk about them here in just a second. It means the concavity changes. That's all that it means. It's a $20 word meaning, oh, it went from being cupped up to cupped down, or vice versa. But look at what I was going to say is look at the first derivative. What's happening to the left of, we know at 0, there's a critical number. In this case, it turned out to be a maximum. To the left of 0, is that blue line above the x-axis or below? So that means the slopes are increasing there. And if you look at the left-hand side, isn't that what they're doing? The slopes are going up. Look to the right of 0. That's below the x-axis. That means the slopes are going down in a negative direction. So you can look at these first derivative graphs, and it tells you a lot. And notice that out here to the right and to the left, that first derivative line is getting closer and closer. It's getting closer to the x-axis. What does that mean? It means the slopes are getting smaller and smaller and smaller. When the function, for first derivative, when the function transitioned between increasing and decreasing, it created those relative extrema. We've seen a bunch of that. And here's where we get to those inflection points. They represent the transitions between concave up and concave down, whichever way it's going. I'll let you read this definition of point of inflection. You could probably translate that to English. If we got C, some point on the graph, and we've got its y value, f of C, and C is a point of inflection, then look what's true. Either the second derivative equals 0 or the second derivative doesn't exist. So a point of inflection is where the second derivative is 0 or non-existent. All right, we want to find the points of inflection and intervals over which the function is concave up and concave down.
Do you want us to find the critical points for derivative 1?
No, we don't need to. I think I did. So the first thing we're going to do, we got to get our first derivative. Now notice this one, I can have a bunch of derivatives. They'll eventually run out because we'll get down to 0. So here's my first derivative. This is the kind of we like to see. So what do? I take that thing and I set it to 0. I don't want to throw anything away unnecessarily. So I'm going to factor out my 4x squared. I've got two factors when multiplied together give me 0, so I can set each one to 0, and here's what I do. There's one of our critical numbers for the first derivative. Now, we don't need it. This problem didn't ask us for it, but I just want to make sure that we know how to get them. And so I do the same thing for the x minus 3. So we have two critical numbers for the first derivative. Again, overkill for what the problem's asking us. Next thing, we want to get second derivative. So I take my first derivative and differentiate it. Now that's the one I want to set to 0. This is getting toward what they're asking us. And I'm seeing some common things I can factor out, which is going to bring us to here. Stop right there for a second. Are we good? So now I've got two factors that when I multiply them together, I get 0, so I can set each one to 0. And y'all could sure do some shortcuts here if you wanted to. So here are my two critical numbers for my second derivative. So I put my number line down.
What about setting where x equals 0 then? Like putting it where x equals 0.
What happens when x is 0?
And there's a point of inflection.
Right. We're going to see the graph of it here in just a minute. Okay, so I pick numbers on either side of 0 and 2 and then 1 in between. So now then when I start putting those into my second derivative, which is that thing, if I've got a -1, then I've got -12 times -3, so that's going to be what? Positive. So I know the concavity is up, right? And then I'm going to do the same thing with a 1. So I would have positive 12 times 1 minus 2. It's negative, so I've got a positive times a negative, which gives me a negative. And so I know that the graph is concave down there. And plugging a 3 in, I've got positive 36 times positive 1. So positive, and we've got back to concave up. So then we reach the conclusion that the concavity, anyway, is this. Let's look at a graph. We'll come back to this in just a second. Here's our original function. I had to zoom way out to get it all the twists and turns on there. Here's our first derivative function. This is, over here, is f of x. The blue line is f prime of x. Now, does it bear out what we've seen before? It touches or crosses the x-axis at 2 points. What about 0? Do we have a tangent line there? Yeah. Horizontal tangent line there. Look what's happening right here. What's that at? X equals 3. Guess what? This point is x equals 3, and then whatever the y value would be for that thing. Horizontal tangent line there. All right, let's add I'm going to take the first derivative line out and put the second one in. Is what you've got for the second derivative, is it supported by this graph? Yeah. Are we okay so far? So what does that mean? So at x equals 0, do we have a point of inflection? Yeah. At x equals 2, do we have one? Can't see it, but it's there. It's interesting stuff, I think, but mm-hmm. Yeah. If it's concave up on a certain interval, and to just continue what you just said, Lexi, look at it around zero. What's happening? The concavity is changing from plus to minus. Around 2, it's changing from minus to plus. So, yeah, just that. Which brings us to kind of toward the end of the notes here. I'm trying to highlight the stuff that really is important. It's possible for the critical points of the second derivative to either be points of inflection or not. So with that in mind, is there a point of inflection at 2? Doesn't there have to be somewhere between 0 and 3?
Yeah.
So odds are it's there at 2. We just can't see it. So you got to use some logic in here. We get to the second derivative test, and look what it's saying. This is even, you're really going to have to go back and read this a few times because you're going, well, that's just what we just found out. No. You got to take this in chunks. This says let f be a function such that f prime at some value c equals 0. Okay, so the first derivative equals 0. Make sure you're seeing first derivative there. And this thing does have a second derivative. Okay, so the first derivative at this point is 0. The second derivative exists. Look what we're doing. What are we plugging into our second derivative here? C. This is not a critical number for the second derivative. It's the critical number for the first derivative. Watch out. This will bite you. We're talking about the same C here. So if the second derivative evaluated at point C is greater than 0, then we got a relative minimum. So we could just skip to a second derivative test for minimums and maximums. A lot of the time, it doesn't always work. So if the second derivative evaluated at the critical number of the first derivative is positive, you've got a minimum, relative minimum. If it's negative, you've got a relative maximum. And then the little kicker down here, if it equals 0, then the test fails. This could be a relative maximum, minimum, or neither one. And then what do? You go back to the first derivative test. Let's do this one. Right now, the only one in class is Sunny, and she's asleep and snoring. So background noise might be a little different in this one. We are going to try to use the second derivative test to look for minimums and maximums here. So the first thing we have to do is to find the first derivative. And once I do that, then I'm going to set that first derivative to 0, so I'll get the critical numbers to start with. I've got some things I can factor out here, so I'm going to pull out a negative 15x squared. And then I've got two factors that multiply together to give me 0. I can set each one of those to 0. And solve for the critical numbers. All right, so my critical numbers are 0, -1, +1. I'm not going to use the first derivative test, though. I'm going to use the second derivative test. So next we have to find the second derivative. Here's the key point. I'm not going to try and find critical numbers for the second derivative. I'm going to use the critical numbers I already have from the first derivative. So I plug in those values, like back here I'm plugging in 0. I get 0. Next, I'm going to do -1. Get 30. And finally, +1. And I get -30. What does that tell me from the second derivative test? It tells me that I've got a relative minimum here and a relative maximum here. It's the reverse of what you'd think. But go back and look at the second derivative test and see what it's telling you. That leaves something, though. What about this 0 up here? If the second derivative gives you a 0 when plugging in values from the critical numbers of the first derivative test, then you've got to fall back on the first derivative test to figure out what's going on there. In other words, the second derivative test failed at that one critical number. So I'm going to go back to here, my first derivative, and I'm going to come down here and use it to see what's going on at 0. Okay, so at 0, I make a number line, and my first thought is, well, let's just plug in -1 and 1. But that's not going to work. Why? And the answer is, those were already critical numbers, and I'm jumping out to them. That's not going to work. So I got to pick numbers in between -1 and 0 and 0 and 1. And so what I'm going to pick is, -1/2 and 1/2. So I'm going to use those numbers to plug back into the first derivative to see what's going on. So at -1/2, so I'm getting that by saying I've got a -15 times -1/2 squared, which is +1/4, times -1/2 squared, which is 1/4 minus 1. So that's where I'm getting the negative times positive times negative. And that gives me a positive. So I put that over here. Then I'm going to do the same thing with +1/2. Well, if you think about it, nothing really changed there. At +1/2, I've still got a -15 times now +1/4 again. And then on the inside of the parentheses, I've got +1/4 minus 1. So I'm getting the same thing I did before, which tells me this. How do I know that at 0, we don't have a minimum or a maximum? Well, I know because the function to the left of 0 is increasing, and to the right of 0, it's increasing. There's a lot going on in this problem. Make sure you understand what it's saying. So let's check and see. Here's the graph. At -1, I do have a relative minimum. At 1, I do have a relative maximum. And at 0, notice the function is increasing to the left of it and still increasing to the right of it. So it's neither a maximum or a minimum. Okay, that problem tied a bunch of stuff together. Make sure you see what's going on.